Now let's take a look at the case where the stock price were to approaching infinity. And let's look at the formula. So we have talked about our expectation last time. Now let's look at whether the formula produces what we expect. So you look at the formula here. So this is the call formula we have. Now, if S naught is approaching infinity, so basically what we have is this part is gonna approach infinity, okay? And this all finite values. So essentially, your D1 is approaching infinity. If D1 is approaching infinity, means that your ND1, which is the area under the normal probability density function, will approach 1. So probability is going to be 1. And same thing for D2. So ND2 is approaching 1 as well. So here you're going to have this being 1 and this being 1. So your call price would just be S naught minus K times e to the power R minus RT. So this is actually what we expect. This is what expected, and the formula will turn out and give us what we have expected. And for put, well, you will see that, you know, this is minus D2 and minus D1. So D1 is approaching infinity, minus D1 is approaching negative infinity, right? So both D1 and D2 are approaching infinity, minus D1 and minus D2 approaching negative infinity. That means this M minus D2 and M minus D1 is going to be 0. And so you have 0 here, a 0 here. That means your put price will be 0. No, okay, so when S naught is approaching infinity, the formula does produce what we expected. Let's look at another case. Actually, let's look at a numerical example to see whether that checks out as well. So if you put in a very large stock price using the same formula that we have shown earlier, that it's 10 times as high as the stock price and as the strike, other things being equal. So your numerical example will give you $900 at the price of the call. And if you just calculate it by hand, S minus this thing here, you actually get exactly the same number. And you will have 0 for the put. So that check out. So that checks out as well. Now let's look at the second one, where if the initial price were to go to 0, that means the company is going to approaching bankruptcy. So expect the call to go to 0 and the put to have a value of K times e to the power minus RT. Well, if you look at it as S goes to 0, this part goes to 0. Okay, so which means that we have the M minus D1 or M minus D2 will approach 1. Okay, because this part is negative infinity, and minus that is positive infinity. So that's why they will approach 1. And if they approach 1, so we have, if we approach 1, so this part will have K times e to the power minus RT. Now, at the same time, this part here is going to be approaching 0 because S is approaching 0 and this one is approaching 1. So the product of this is going to be 0. So we have this P will have this value there, k times e to the power of minus RT. For call, well, for call you have this because it's positive here, so it's minus infinity, and d1 is 0, and d2 is 0, so your call here is going to be 0. So that's basically what we expected. Let's take a look at the numerical example. So you have S, you just put in a very small number here compared to the strike price. You will see that the call value calculated numerically through the formula, it's going to be 0. And the put is going to be 99.24, and which is the same value, almost the same value of this k times e to the power minus RT. There's a little difference, it's just numerical difference there, round off errors. And again, the put call parity condition checks out as well. Now, look at the last example here. If the volatility were to approach 0, so basically your stock stuck somewhere not moving, so you would expect that either it's gonna have some positive value or it's gonna be 0. So if S is greater than this part, then you'll have a value, right? For call. If S is smaller, you have 0. But if S is smaller than this part, you have a value for put. Otherwise, you have 0 for put. So then you look at that. If volatility were to approach 0, if this term is greater than 0, or you say that if S divided by k times e to the power RT, basically you raise this power here. You can do that because this is a monotonically increasing function, right? So you can do this. So if you e to the power of this thing, you'll become this, and so they have the same condition. So if this is greater than 0, that means this is greater than 1. And if that is the case, then you would have D1 approaching infinity, D2 approaching infinity, which means you'll have this being 1, and D1 and D2 being 1. So your call will be S minus K times e to the power minus RT. Or if log S naught divided by K plus RT is less than 0, or which means this thing is less than 1. This thing less than 1 meaning S naught times e to the power of RT is less than K. So S naught is S naught times this thing less than K. Then so S naught times e to the power RT less than K means that K times e to the power minus RT is greater than S naught. So in that case, you have a 0 here because your ND1 and ND2 is going to be 0. Okay, then so in that case, so you have a if ND1, ND2, if D1, D2 approaching negative infinity means minus D1 and D2 approaching 1. So that means if this condition is materialized, your P will be equal to K times e to the power minus RT minus S naught. Otherwise, it will become 0. Okay, so that sort of check out what we expected. Then numerically, you can see that if you put in a volatility of 0 here, then the case we have here is S is greater than the present value of the strike price. So in this case, we're a case here, this case here. So you expect the call price to be like this and the put price to be 0. And that's exactly what we have. The put price is 0. The call price is equal to S minus the present value of the strike price.